In the previous two FPGA lesson videos, some of the FPGA applications I showed you were pretty boring and could easily be emulated with a microcontroller. However, the point of those videos were to give you most of the tools and concepts you need to move on to more advanced applications. This video will be an example of one of those applications. In this video, we will be building our very own single-channel oscilloscope that will auto-trigger on incoming UART messages. The design will also interpret the waveform concurrently and display the Ascii values on the 7-segment displays. Surprisingly, this won't be as difficult as you might think. We'll be using the Mercury FPGA combined with the new baseboard and an FTDI breakout board. Like the previous videos, we'll be covering a bunch of new concepts here. We'll learn how to interface to the analog to digital chip on the Mercury, interface to a VGA port, create a UART receive module, synchronize incoming asynchronous protocols, create multiple processes in a single VHDL component, and finally, how to drive a 7-segment display. As always, I'm just going to start by creating a top-level design to create this oscilloscope application. The peripherals I'm using in this oscilloscope are the onboard button for reset, the clock 50 MHz to synchronize everything, and the analog to digital converter IC located on the Mercury board. The analog to digital converter is going to hook up to the FTDI USB to UART breakout board, which is going to be connected to the computer. For the output, I have the VGA port and the 7-segment display port. So the two biggest components in this project are the analog to digital converter and the VGA component. Now for a big project like this, sometimes it's easier just to borrow someone else's code that they created to implement or drive this kind of functionality for you. And that's what I did with the VGA component of this project. For the VGA component, I chose yet another VGA project created by Sandro Amato, and this is available on the OpenCore's website. This yaVGA project contains waveform generation that you can use, and also some character mapping so you can also write characters to the VGA screen that you're connecting to. So with the original project, unfortunately I had to remove the character mapping stuff because it was too big for the Spartan 3A. After I removed everything, it was able to fit, but I also had to hard code the grid lines in, and I also spared the waveform generation functionality. So I'm going to put the derived module here. So here's the derived yaVGA project that I added here to interface to the VGA monitor to drive the waveform functionality and just to get things to pop up on the screen in general. So let's do a quick black box analysis of what this module can do. For the inputs, you have the clock and reset. So the clock needs to connect to 50 MHz, and reset's pretty obvious. Just set to 1 to reset the module. These enable lines, I've learned you need to tie up to high in order to get this to run. And these 4 inputs here are how you interface to the waveform functionality of the yaVGA. Basically, data is the y-axis and address is the x-axis. So at any given address, you write y data point. So pretend this is your VGA monitor. Address is going to determine how far along the x-axis you are, and data is going to plot where here is. So if you were to increase the address while you are increasing what you write to data, then you would just kind of get something like that, where you would start from the top, 0, and to the other extreme. Now, when you want to write data to a specific address, you need to have the write enable high. So if you want to write data like 1F2E at address 300, you would need to set 1F2E here and then 300 here, but then you would also need to raise write enable high. Otherwise, the data will never get saved to that address. And then the clock, for the clock, you can kind of drive that with whatever. Ideally, you would synchronize this clock with the waveform, but in my experience, you can hook this right up to the same clock as here. Now, the outputs make perfect sense because that just hooks up straight to the VGA port, which uses horizontal sync and vertical sync. I'm not going to go over the protocol of VGA because there's just so many tutorials online that cover this. So if you're interested in learning how the protocol works, then you can easily Google search that online. But just know that what I'm going to do is I'm just going to hook up this single red signal to all these reds this green signal to all these greens, and this blue signal to these two blue signals. And yeah, these are only 1-bit values, so you really only get 3-bit color or 8 different colors with this setup, but that's made so it simplifies the application down. So that was a quick black box analysis of the yaVGA, and now I'm just going to do the same type of analysis on the MercuryADC. This MercuryADC module is supplied from Micronova, and you can get it on the resources page on their website. So what this module will do is that it interfaces with this ADC, which communicates through SPI. And then you can pass the channel that you want to read from. So this ADC has 8 different channels on it, so you can read from 8 different sources. So that's what this does. You can pick which one of those 8 channels that you want to read from. The diff-n input a differential read or a single-ended read. If you want single-ended, you have to write it to 1. In this case, I'm going to use single-ended. Trigger is what you use to pulse high to tell the MercuryADC to begin a conversion with the ADC. So when you give a pulse high here, the Mercury with its SPI interface will talk to the onboard ADC IC and obtain the ADC reading for the channel that you specified. Now when it's done with its conversion, it'll put the result on D out here, and then also pulse out val. So this is actually a pretty perfect application for a register to hold whatever value comes out from here. So you can see I added the register here to receive the value of D out from the MercuryADC. Now before I introduce the rest of the components, let's think about what we want to accomplish for a second. We want to build an oscilloscope that auto-triggers on the falling edge of the first start bit of 9600 baud UART signal. Then we want to display the entire waveform in a good proportion to the rest of the screen on a VGA computer monitor. Then when the waveform is captured, stop creating the waveform. So the logic is actually pretty simple. If the ADC here drops below a certain value, then start capturing, which means write 0 into this address, then raise the write enable signal and record the data point. Then after a specific amount of time, increment the address to 1, write a new data point to that address, and keep write enable high. After we capture the entire screen to address 800, then we stop. When we stop, then we want to wait for the next start bit. So I pretty much have my input interface here and my output interface here, and what I need to do is I need to bridge this input to this output in such a way to accomplish the oscilloscope application that I want. So what I'm going to do is I'm just going to fill in everything all at once, and it's just going to be a little overwhelming at first, but I'll kind of hold your hand through the explanation through it. So this is a significantly more cleaned up version of what I use to accomplish the oscilloscope application that you see in the example at the beginning of the video. Like I said before, this probably looks very overwhelming at first, but it's actually much easier than it looks. If we review what a UART signal looks like, you have this initial start bit. It starts off high, then you get the start bit, and then these are just arbitrary data byte bits that could be any value. Then you have the stop bit, which is always 1. So let's just kind of walk through the process of what happens when a UART signal is received. So we send some byte through the computer, through PuTTY or something. It reaches this FTDI, it converts it to UART. So we get this waveform that's going to be generated onto here, going to this ADC. Starting with the clock div, I have clock divide 86, which basically just is a clock divider that outputs a slower clock signal than the 50 megahertz clock. And you can see the output of this clock divider feeds straight into the trigger. So that means this MercuryADC is constantly triggering over and over and over again. So what's happening is that it's constantly reading this input right here. You can see I'm hooked up to channel 4 here, which is the channel that I plugged in Actually, channel 4 is wrong. This should be 5. I'm hooked up to channel 5. So I'm constantly reading channel 5, which the FTDI is plugged into. And I'm getting a single-ended input. So that's all that I did with this MercuryADC. So it's constantly sampling over and over and over again, and it's constantly outputting a new value to this register. Now this register is hooked straight up to the data input into yaVGA, but it also hooks up to this FSM logic analyzer. And all this thing does is it just looks at this value and waits for that drop. So when it sees that the ADC is at one value, but then it drops to the next value, then it just uses a simple go signal to say, okay, now we have a start bit, so let's start capturing. That's all that this thing does. So you could have some output coming from here, but then once it drops below a certain value, then it raises the go signal, which you can see connects to write enable, which makes sense because we're going to start capturing. So if we raise write enable, then that means we're going to start capturing. But Go also attaches to this count 800 device, which all this does, this is actually a bit misleading because it actually counts from 100 to 800, and 100 to 800 is outputted here. So what happens when we receive the start bit, it will raise Go high, it will see that Go is high, so the address out counts from address 100 to address 800 and connects to here. Now all this does is once it gets to 800, then it outputs stop, and then stop connects to here, and then the FSM sees that we reached 800, then it lowers Go again, and that's when we stop. And you can also see the clock divider connects here. It drives kind of like the timing. So count 800 appropriately counts a defined rate that I want. I don't want it to capture the waveform too fast or too slow. I want it to capture a specific amount. So the clock div 86 module is the module that determines the rate at which I sample the MercuryADC and record data points with the counter so that the 9600 UART waveform fits nicely on the screen. So how was a division of 86 chosen? Well, when the waveform is captured, I want it to be centered on the screen. So let's say this is my VGA monitor. When I capture the UART signal, I want it to be padded by 100 pixels on the left and 100 pixels on the right, so it fits nice and evenly. So start off high, and then there will be the start bit, and then there will just be whatever bits are just sent over UART. So I kind of want it to look like that, where start bit, data bits, and stop bit. So that's one reason why I start at address 100 on the counter module, and then I only want to sample this waveform fast enough where I approximately get this end of the stop bit at address 700. Because if I sample too slow, then the waveform is going to be really tight and condensed, because it's just going to appear as a short amount of time. And if I'm too fast, then the waveform is going to be stretched out, and then I might miss a component of the waveform. So it's important to figure out the correct sampling rate at which I want to grab this data, so that way it fits nicely on the VGA monitor. So 9600 baud means that it takes 1 divided by 9600 equal to 0.104 milliseconds to transmit a single bit. Well, there are 8 bits plus the start and stop bit. So you multiply that value by 10, which is just going to be 1.04 milliseconds. So the entire waveform of the UART message will take exactly 1.04 milliseconds. Now, if I want the beginning of the start bit to start at address 100 and I want the end of the stop bit to end at 700, then I have 600 data points to sample the waveform. So 1.04 milliseconds divided by 600 is just equal to a rate of 1.736 microseconds per pixel per address across the screen. So every 1.736 microseconds, I want to record a data point, then I want to wait another 1.736 microseconds and record another point, and so on and so on. Now the FPGA clock is 50 megahertz, and the period of that is 20 nanoseconds. 1736 nanoseconds divided by 20 nanoseconds is 86.8 clock cycles. So it's going to take 86.8 clock cycles to reach 1736 nanoseconds. So I want to record a data point, count 86.8 clock cycles, record another data point, wait 86.8 clock cycles again, and record a data point all the way up to address 800. Now in the module, I just simply round this down to 86. And there's a reason why I rounded down instead of up. But I'm going to just cover that later. Down here is where I have the method where I read the UART waveform and display the waveform on the 7-segment display. As you can see, it's a completely parallel process. The oscilloscope portion functions independently of this UART to 7 segs hardware. This is a powerful characteristic of FPGAs. Microcontrollers have time constraints, whereas FPGAs have spatial constraints, which means there are no nuances whatsoever in adding this additional hardware here. All it means is I'm going to be taking up more space on the FPGA. So you might notice that this section of hardware is connected to a different pin than the pin that's connected to the analog to digital converter. The FTDI is going to be wired to both the ADC and a digital pin on the FPGA. This sync hardware is something I use for all protocols, especially asynchronous ones, and do not underestimate the importance of this piece. So let's say the waveform starts off high, but then there's a falling edge. So it kind of looks like this, and we'll say the clock cycles of the clock that runs this hardware occurs here. Now since the falling edge here occurs at different times than the rising clock edge, that means it's asynchronous. This sync hardware simply buffers the signal and forces this edge to one of the clock signals, making an asynchronous signal into a synchronous one. The sync hardware adds 2 clock cycle delay to the signal, so the output will become something like this. So here you can see it takes 2 additional rising edges of the clock until this falling edge is propagated. So this probably seems kind of useless at first, and I wouldn't blame you if you thought this was pointless. Counterintuitively, this is actually extremely important. I personally have been pretty badly burned by not using these sync hardwares, and I would have really strange symptoms that exhibited seemingly impossible behavior. So it's best to kind of save yourself a headache and add the simple sync piece to your design. So like I said, the sync hardware just matches the rising and falling edges of your input asynchronous protocol to a rising clock edge. Now the synchronized UART signal gets fed into here, and this RX UART signal basically just understands the UART protocol being received at 9600 baud. Now when it's finished, it will output the data to this register, and this register will input the hex values to display on the 7-segment LEDs here. And this module interfaces to the A to G LED segments and the enable digit lines. So now that I kind of did a very generic overview of how all this stuff works, we're going to dig into the actual VHDL and kind of quickly derive these devices. We're going to add the MercuryADC and the yaVGA to the project, and then finally create a top level to contain all these modules. So kind of like in the past, I explained what these modules are going to do in the top level, And then in the VHDL component of the video, I explain how these components accomplish what they do. So before I start, I'm going to say that for these three pieces here, since they're kind of tedious to implement in VHDL and it'd be kind of a pain to wire all this up in the top level, what I'm going to do is I'm going to create a surrounding VHDL module that encapsulates the functionality of all three of these components in a single VHDL module. In the past, I've shown that a VHDL module has a process that helps carry out the logic. Well, you don't need to only use one process in VHDL per VHDL module. You can use as many processes as you want. And so in this case, I'm going to use a process for each one of these components. So just kind of a heads up on that, that's what I'm going to do here. I already have all the VHDL implemented. To save on time, I'm just going to step through the design that I made so that way you can understand how this was developed. Now first, I'm just going to explain how I hooked up the MercuryADC and how I hooked up the yaVGA project, which is here. The yaVGA in this case is called the VGA controller, which is this component here. In the section where I wire the inputs and the outputs to these devices, for the Mercury, I have the clock connected to the clock pin of the FPGA. The clock pin isn't shown in this diagram for simplicity, but it's there. And this clock is meant to hook up to the 50 megahertz clock on the FPGA. Trigger connects to clock slow, which is a signal name of the clock div 86 output. Diff-N connects to 1, like I said. Channel connects to 5. D-out connects to SD-out, which is going to go to this register. And out-val low connects to the load signal of the register. And these ADC, MISO, MOSI, clock, or chip select and clock, those are the SPI pins that interface to the ADC and are the inputs and the outputs to that SPI interface. And as you can see, they're up here. And those are simply declared in the UCF file here. So that's how the MercuryADC is hooked up. The VGA, the yaVGA project, is hooked up with the clock input up here connecting to the FPGA clock, the 50 megahertz. Reset connects to the user button, which is the name of the onboard Mercury button. The output horizontal sync connects to the HSync output in the UCF file, and the VSync output of the UCF file connects to the vertical sync output of the yaVGA. So output VSync connects to VSync in the UCF. The output red connects to signal red, output green connects to signal green, output blue connects to signal blue. And kind of like what I said before, these output colors are only 1 bit each, so output red's only 1 bit, and I wanted this output red to connect to all 3 pins for red on the VGA. And you can see I did that here. Red, the red top level output 2 down to 0, these 3 pins are all connected to the 1 signal red single bit output of the yaVGA. And the same thing for green, and the 2 outputs for blue in the top level, that is connected to the 1 signal blue output of the yaVGA. The input wave data connects to the register. SWaveD is the name of the signal. SGO connects to the iWave enable, the right enable pin here. That's the signal name for that signal. The name for this signal is SGO. And for the wave clock, I just connected that straight to the same clock that this pin is hooked up to, so the 50 megahertz FPGA Mercury onboard clock. Then finally I have the S counter out, which is the name of this green signal here. This green signal connects to the address in to determine at what address do I write a waveform data point to. So as I mentioned, I'm going to take these 3 individual components and make each one of them a process that's embedded in a single VHDL module. And the single VHDL module is here. It's called the FSM yaVGA controller. And the inputs and the outputs are up here. And if you look, I have clock input, reset input, input from the analog to digital converter, the output go signal, which connects to wave right enable, the output trigger that comes from the clock div 86 process, and that's going to connect to the MercuryADC, and the output address coming from the counter to hook up to the address on the yaVGA. Now notice that I don't have a stop signal input or output because the stop signal in this case is completely internal within this module. So if we look here, I have the clock div 86 process, the finite state machine process, and the count 800 process. And I'll just go through each of these really quick. Clock div 86 activates on clock signal. On the rising edge of the clock, if the count is less than 43, then increment this signal value. Now when it gets to 43, set it back to 0, and then not this S clock div 86 signal. And this S clock div 86 signal is going to be the driver for the signal here. And you can see at the bottom it connects to the trigger output on this VHDL module. It connects to trigger. That's 43 because I'm knotting, and it takes 2 knot operations to make an entire period. So in order to divide the input clock by a factor of 86, I need to count to 43 twice. Now moving on to the FSM, as in the lesson 2 video, I'm using a finite state machine, which just consists of 4 really simple states: an initial state, wait for start state, state go signal, and state stop signal. Starts off at state initial on resets, and on power ups it will start off in this state, and it'll just make sure that the go output is low so we're not writing any data to this yaVGA. And then we're going to go immediately to the next state, the wait for start state. And this simply just waits for the start bit on the UART signal that's coming in from here. So I take the lower 10 bits, and to check for the start bit, I check if the input is greater than 200. And you might think that I want to check if the start bit is less than 200 because I'm checking for the start bit. So I'm going to be looking for the falling edge. If this is the UART signal, I want to look for the falling edge. But in reality, what I did was with this register, I actually inverted the signal so that way if I get a high value coming from the MercuryADC, that it outputs as a low value, because on the yaVGA, a data value of 0 is towards the top, and as you raise the data value, you get lower. So if this is your VGA monitor and you're increasing data and address at the same time, like I said before, it will decrease. So 0 starts off at the top. And so what I kind of wanted to do was invert that. So I used this module to invert the value coming from here. So that's why I check when the ADC is greater than 200. Then I move on to the next state, which it's at this condition that I know that the start bit has been received. Otherwise, just stay in this wait for start state. Then in the next state, just raise go high. So make this signal high, enable the right enable, and then go immediately to the next state. And then all this does is just wait for the stop input coming from here just to go to 1. And then once it hits 1, then it knows that it's done capturing, so it's going to go back to wait for start. Otherwise, just stay in this state. And the last process is the count 800 process, which obviously represents the count 800. And so it's going to control the stop signal, which goes to the FSM, and the address output. And so in this case, it actually triggers on the signal clock div 86, which makes sense because in the diagram, it's driven by the slow clock outputted by this module. Now in this process, so it activates every time sclock div 86 gets changed, it checks for the rising clock edge of the signal. So if if the signal go becomes 1, which means that a start bit has been detected, then check to see to make sure that the S wave address that gets written out here, you can see S wave address gets written to the output address. Check to make sure that you're below 800, and if you are, increment S wave address by 1 and keep the stop signal out here 0. But then once you get to 800, then raise the stop signal high so that way this FSM knows to lower the go signal back down to 0 so that way you're not writing to the monitor anymore. Then once the go signal goes back low, then we want to reset the address output coming from here back to 100. This is 100 in binary. And just keep stop low at that point. So it kind of makes sense because the MercuryADC and the count 800 are synced at the same time. So this MercuryADC begins a conversion at the same exact moment that a new address is written into this input. So that means for every instance that the MercuryADC is triggered, the result of that process will get written to the data to yaVGA. So I think the next component I'll go over is this register right here, which is the only part left of this oscilloscope application. So really just with these 4 modules, I have the oscilloscope application. The other 4 handle the UART to 7 segs. And that guy is here. It's kind of your typical register. It takes 10 bits in and 16 bits out, and I'll show you why in a second. So on reset, it just resets the data output back down to 0. If load goes high, then 512, and then I concatenate a 0 with 9 down to 1 of the input data that comes in from here. And the reason why I go 9 down to 1, I'm basically just dividing the analog to digital converter by 2 and concatenating the 0 so it's still the same length as 512 in binary. The reason why I do this is just through testing. I found that the result from here was way too sensitive, so I divided it by 2 so that way the waveform would fit on the screen, because what I would get is I'd have this as my VGA monitor, and so the UART signal would just be off the screen. So by dividing it by 2, I was able to get it to fit within the boundaries of the screen here. So that's why I divided it by 2 by shifting it down. And I inverted it by subtracting that value from 512. So that's all there was to it to the oscilloscope application. You could see that even though it looks pretty complicated, it actually in reality it was pretty simple. So now I'm just going to go over these last 4 components, which takes the digital UART signal waveform input and interprets it and displays the value onto the 7-segment display. And as you saw in the demonstration earlier, that what it does is it will display the most recent value received on the less significant byte end here, and then the previous UART signal will be stored here. and it just gets shifted in. And that's actually fairly simple as well. So I'll start off with the sync hardware, which takes the asynchronous UART signal and makes it synchronous to the 50 megahertz clock. And that component is here. It's called the FF UART RX sync, and the reason why it's FF is for flip-flop. And basically all it does is it has these two signals which are initialized at 1, and on reset it's also initialized at 1, so you might be kind of wondering why it's default high, but I explain it here. I want to make sure that the output coming from here is high for the UART signal and not low, otherwise the RX UART would interpret the low value as a start bit. So on every rising edge of the clock, what happens is it takes the input. UART RX is this input, and it has clock and reset as always, and then the output UART RX sync is this output. So what happens is this input gets passed to this signal, and that signal gets passed to the FF2 signal, and then FF2 gets passed to the output. Be kind of confused by this because you might think that, well, what's the point of having this? Why don't you just sign UART RX directly to SFF2? Well, if this is something that you're confused on, that means you're still stuck in the software mentality and you need to remember that this is hardware. So what's happening is that both these instructions are being executed at the same exact time. The FPGA doesn't execute this one first, then execute this one second. Both of them happen simultaneously. So it kind of acts as a shift, basically. UART RX gets shifted into FF1 the same exact time FF1 gets shifted into FF2. And kind of like how I explained before, how if these red are your rising clock edges, and this is your asynchronous waveform, I mentioned that it's 2 clock cycles behind. Which makes sense now that you see the application because you have 2 signals. So on this clock edge, this green is being passed to FF1, and then on this clock edge, FF1 is being passed to FF2, and FF2 goes to the output. I'm going to move on to the RX UART module, which will take the synchronized UART signal, and when it's done parsing that signal, then it will take the resulting data byte and store it in this register. So this is the RX UART module, which carries out the RX UART component there. It has the input UART RX, which is the synchronized input here, clock and reset as always, and then the output RX data, which is, you can see it's a byte long, and then the load signal to signal the register that's connected to it here to load the data byte coming from. So it has an initial state, start bit, so it waits for a start bit here, then it waits 1.5 baud, samples a bit, counts to see if it's received 8 bits, waits another baud, then it has a cleanup state and a wait out the stop bit state. So it's got the asynchronous reset. So on every rising clock edge, starts off in the initial state, then goes immediately to start bit state. So this input UART RX, which again is the input coming in here, it's going to wait for that to go to 0 for a start bit. And until that goes to 0, it's going to stay in this state. Okay, so then after we move from start bit to wait 1.5 baud, which will happen once we receive that start bit, we'll get here. So what's going to happen is that in this state, it's basically kind of a delay where we want to wait 1.5 baud lengths. But why do we wait for 1.5 baud? Well, we have to remember that we're starting this state right when we receive our start bit. So let's say that this is our input waveform, the UART waveform that's coming in, and that this is the start bit. And this is the start bit, which waits for 1 baud length, and then the first data bit. Well, what we want to do is, since we're starting wait 1.5 baud right here, we don't want to wait 1 baud length, because then otherwise because the next state is going to be sampling, and we don't want to sample this waveform right at the edge like this. We want to make sure that we're sampling the waveform right in the middle of the first data bit. So when this state is activated here, it's going to wait 1.5 baud lengths. So that way, when it exits out of this state and goes to sample bit, we will be at a time where the middle of the first bit is currently on the input. So it just uses this baud counter and counts to a constant, which is set at 1.5 baud, and then it goes to sample bit. It resets baud count to 3 because we have to accommodate for these extra states that we're entering in, because if I set it to 0, then I'm wasting time going through other states. So I want to accommodate for the clock cycles, which are being taken up by this state, the count 8 state, and the wait bauds, or in the wait baud state here. So what's going to happen is that there's this UART RX data signal, which will be shifted in with this input. So the input here, it's going to take whatever is on here and shift it into this signal, which is 8 bits long. And it's going to, take 7 down to 0. So the UART RX gets shifted into the most significant position. And then it increments bits sampled, because we're going to be looking for 8 to make sure that we didn't reach 8 bits sampled. Then we're going to move on to the count 8 state. Oh, but first let me explain that UART RX data gets passed to the output here. So UART RX data is actually being pushed out here, but it never gets written to the register until we write load high, remember. So in count 8, what we do is we look at S bits sampled and check to see if we're at 8, and if we are, then go to a cleanup state where we finish up. If not, then go to a wait baud state, and we just wait 1 baud instead of 1.5 again, because since we sampled in the middle on this first data bit, we want to ensure that we're still in the middle for the second data bit when we sample. So then it transitions to the wait baud state, which waits a single baud length, and then once a baud length has been counted, it goes back to sample bit, which shifts in from the input again to UART data, increments the S bit sampled, and checks to see if we have 8, and repeats this 8 times until we do have 8 bits sampled. And then what will happen is that we go to the cleanup state, which will set sreg UART load high, which connects to this output, and the output goes to this register to load the data that's on this output. And then it resets baud count, resets bits sampled, and goes to the wait out stop state. So once it's in state wait out stop, what we want to do is we want to wait for the stop bit before going back to the initial state. And you might think that we should go to the initial state right after cleanup because there's nothing left to do. We already have the data that we want. Why don't we just go back to the initial state? Well, that would work, except for the time where your final data bit is equal to 0. Because what's going to happen is that, so I'm going to draw the tail end of the UART signal. So let's say this is the 7th data bit, and then this is the last data bit, the 8th data bit, and it's low. And then you get the stop bit. So the red is the stop bit. What will happen is that we sample here, then we clean up, and then come here. And if we were to go straight to initial, then what would happen is that very, very soon after resample, we're going to be checking for the start bit again. And what's going to happen is that it's going to see that the UART line is low. Then it's going to start this whole process over again and get some faulty reading. So what you want to do is after you sample and after you clean up, then you want to transition to this wait out state, where you wait out the stop bit here, and it's going to look for the rising edge. So after you load the register, set the load signal back down to 0, and until the input of the UART signal goes high again, then stay into this wait out stop state. But then once UART goes high, then go to state initial, and then we can wait for the next start bit. So I'm just going to explain this register now, even though it's very simple. It's this guy. So the one special thing, like I said, is that what we want to do is we want to shift our bytes down into the 7-segment display, and so this register is what accomplishes that. So everything else is very standard, very simple, except for, well, it takes in 1 byte and outputs 2 bytes. So what happens is it takes the input. Every time you load the register, it takes whatever's on the input and concatenates it with the signal UART data. And it only takes the least significant byte and shifts it down and puts the input into the least significant spot now. And then that signal just simply gets passed through to the output. Now I'll move on to the quad 7 segment driver. And this quad 7 segment driver, it is another module that I created which has multiple processes in it, so we can see the application of that. And that module is here, and you can see it has clock and reset inputs, which are pretty general. I didn't include them in the diagram like most of the modules for simplicity. Then the input to display, which is here, output A to G segments, and the enable digit lines. So I created several processes in this module as well, and to break down the processes, you could kind of try to break down what you want to accomplish. So as far as processes go, well, I'm not sure if you're aware of how 7-segment displays work, but I'll just give a quick explanation of how these work in case you don't. Basically, the general approach to driving these 7-segment displays is because this A to G controls the segments for all of these digits. So if you're to show a 1 on A to G, it's going to show 1 for every single digit, not just one of the digits. Same thing for E or 9, it gets displayed on all of them. So what you're supposed to do is you're supposed to use this enable line, which is active low. So what you do is you can independently turn off any of these. So what you do is you turn on this one for a short amount of time, use this to display what value you want there really quickly, then quickly mux to the next one, then display whatever digit's supposed to be there, then here, then here. So you alternate. So you display this digit, turn off the rest of them, display this digit, turn off the rest of them, display this digit, turn off the rest of them, display this digit, turn off the rest of them. And you do it so fast that the human eye can't see or can't notice the blinking that's going on actually in reality. So what you want to do is you want one process to handle what gets displayed out here depending on what digit is currently being displayed. You want another process to control when these displays get turned on and off, and then I'm going to create another process that controls the rate at which we mux through these digits. So I'm going to start off by explaining the processes in here. What I do is I have this counter process that handles the rate at which I multiplex through the digits. And what I do is I just take this giant signal counter and I just sample out the most significant 2 bits to determine which digit do I display at what time. Because I take advantage of the fact that there's 4 digits to mux through, and that 4 can be represented uniquely with 2 bits. So on every rising clock edge, this gets incremented, and this mux signal only gets assigned these 2 bits, like I said. and this signal is used throughout the rest of the module as a way to tell which digit to display. So when these two are 0, 0, then it's going to display the first digit, 0, 1, second digit, 1, 0, third digit, 1, 1 is going to be the last digit. Now this process handles purely this output, so it uses the multiplexing bits that I have. If the multiplexing signal is 0, 0, these are active low, so that means what I'm doing is I'm assigning SAN, which gets passed out to the output. If it's 0, 0, it's going to be 1, 1, 1, 0. And this line is active low, meaning that 0 is going to activate the first digit, and you can see in the comment. And if it's 0, 1, display the second digit, turn off the rest. If it's 1, 0, display the third digit. If it's 1, 1, display the most significant digit, and turn off the rest of them. So this process is really easy. And then this process might look a bit cryptic, but it's actually also pretty easy. If you are currently displaying the first digit, what I want to do is I want to take the lower nibble of this input, so the least significant 4 bits from this input. The least significant 4 bits from that input, convert it to an integer, and then use that as a pointer in this lookup table, which goes from binary to segment. And then whatever the result of that is gets thrown out on the output to determine which segments here to display. So how does this work? Here's the lookup table. So here's how 7 segments are broken down. It goes A, B, C, D, E, F, G. So seven different segments to light up. So what happens is that for 0, if I want to display 0, you can see I actually have 8 bits here instead of 7, because the 8th is for the decimal point. So how it goes is decimal point A, B, C, D, E, F, G. And 0 is to turn the segment on, 1 is to turn the segment off. So for 0, if we want to display 0, I have 1, which means don't turn the decimal point on. 0 for A, 0 for B, 0 for C, 0 for D, 0 for E, and 0 for F, but keep G off. So if you look at the green, you can see I formed a 0. And I'll just do a few more examples so you kind of get the hang of it. 9, no, let's do 5. So turn off the decimal point. A is on, B is off, C is on, D is on, E is off, F is on, and G is on. So you can see that makes a 5. And it continues like that, so 0 through F for hex. And so that's all this does, is it just takes the values from here and just uses a lookup table. So the lower nibble of this input is in decimal 5. Then what's going to do is it's going to point to this, which is going to return these segments. So on this digit, display these segments. That's all it does. So it's kind of funny how something so simple can actually do something pretty powerful, and that's all you need to do to get the quad 7 segment driver to work. So the top level is nothing special. If you've seen the last video, the lesson 2 video, you know kind of how tedious these can be. So it's just a matter of declaring all the components that I showed you in the top level up here. It's just a simple matter of declaring all the components that you see here. And yeah, this section, after this begin, this section is just wiring it all up. The top level is always kind of the most boring and the easiest one to do. So this one's pretty self-explanatory. So when you build this project and import it, I mean, this should build right out of the box. There's really no reason. Just make sure that you have the right device selected up here, and that when you have this module, this one should be set as your top module. You can see these modules have the option to be set as a top module. This VGA top level should obviously be the top module. That should automatically be done for you, but just in case it doesn't, you need the baseboard UCF file to abstract the inputs and the outputs of the baseboard, so that way you can have nice, clean, easy to understand names like this. Of course, what you have to do is you have to right click on process properties and make sure you have allow unmatched LOC constraints checked. Otherwise it's going to fail for you, and it might be weird why. Yep, this one will generate, and then all you have to do is use your Mercury programmer to get the VGA top level bit and just simply burn that straight to the Mercury board. Before we look at the product of our work, let's take a moment to let what reach is accomplished soak into our minds. If you've seen all my FPGA videos, you might now be realizing which applications will outperform a microcontroller, and when you should use an FPGA in your project. In my experience, there are two big situations where a hobbyist will want to use an FPGA in his or her design. The first situation is when you require parallel processing that can be executed very fluently. Take our oscilloscope example. We have our own drivers for the SPI protocol, a VGA protocol, and we created a driver for receiving UART. 3 protocols being handled simultaneously with ease by the FPGA. Then we drive a set of 4 7-segment displays with a small bit of logic up here. The crazy thing is that we barely took up any space on the Spartan 3A with this application, and you could easily just create multiple instances of this top level and have multiple oscilloscopes running in parallel with no caveats. The only limitation that you have is when you run out of lookup tables on the FPGA. Let's compare that to a microcontroller. The microcontroller very likely has its own dedicated hardware to SPI and UART, so no problems there. But then once you get to the VGA, I've personally never seen a microcontroller having hardware to drive a VGA protocol. So you'll have to bit bang this protocol. But if you bit bang, your software is pretty much locked up setting its timers so it knows when to set the pixels at the right time and when to activate the horizontal sync and vertical sync lines. So because your software can only do one thing at one time, you can pretty much forget about driving a quad 7-segment display. You'll have to get an external driver chip to drive these segments for you. Then you'll have to implement this logic, which should be doable but would be a pain. But remember how I said on our single FPGA we could copy this design several times? Well, there's no way you could do that with a single microcontroller. You would have a difficult enough time doing this one instance. It would be impossible to implement a second. But being on the topic of bit banging, that brings us to my second situation where FPGAs can trump microcontrollers. And that is when you're supporting special hardware. The VGA is special because it's not supported by microcontrollers. But with FPGAs, we can just create the hardware driver ourselves. But let's look at another example. If you saw my Bluetooth N64 controller prototype, you would see that I used an FPGA to talk to the N64 console. Well, that was accomplished through this design I created. The N64 console uses a proprietary asynchronous half-duplex protocol that isn't supported by microcontrollers. But with the FPGA, I was able to create the hardware drivers myself right here. I was also able to integrate my own open collector output and input hardware here to implement the bidirectional nature of the protocol. And in parallel to all that, I have a UART module running here. Now, since I only took up 1/10 of the space on the FPGA with this design, I can simply copy this entire hardware for the rest of the 4 controllers. So now that I have those afterthoughts out of the way, let's get back to the oscilloscope. So I got all the physical hardware set up. Here's the FTDI chip. It's on a breakout board provided by SparkFun. This yellow wire over here is a shared ground between the Mercury baseboard and the FTDI chip. Then the yellow over here just kind of breaks out the TX pin coming from the FTDI and goes to just the wire, the white and green wire. The green wire goes to the analog to digital converter chip on channel 5, and the white wire goes to PMOD 0. And that's, the white wire is the digital read to get displayed on the 7 segs. The FTDI is also powered through USB and connected to my computer right now. And let's take a look at the VGA monitor. Alright, so you can see the VGA output coming from the Mercury baseboard. And I have 10 blue horizontal grid lines that I hard-coded. And those are going to denote the start and stop bits and the 8 data bits in between. So I have I have PuTTY open up right here on my computer, and it's opened up on COM7, which is this FTDI chip. And so on my keyboard, I'm just going to type in the spacebar, and you can see, might be a little difficult to see, but you can see 20 appeared on the 7-segment display, which 20 is the Ascii, which is the ASCII character code for the spacebar. And you can see 20 appears here, the most significant bit starts here, and then it goes to the least significant bit here. As I said before, this is the start bit and stop bit. And you can see I have about 100 pixel cushion on either side, and so the waveform fits really nice and perfectly within the VGA monitor, at least horizontally. So like I said, it reads 20, it goes 00102 00000, so 20. 0, if I actually push the key 0, I'll get 30, which appeared on the 7 segs, and then you get 0011, which is 3, and then zeros for 0. And 1, 2, 3, 4, 5, 6, 7, 8, 9. And even if I type in a bunch of random characters on the keyboard, it'll still be able to well, at least it perceives to keep up. I hope you enjoyed the video. I hope that application that I showed here is a good demonstration of how powerful FPGAs can be. And thank you for watching the entire video. If you liked the video, if you learned anything, please give me a thumbs up. I really appreciate any feedback. And take care.